What if the picture you carry in your mind of the solar system is only a convenient sketch, not the structure itself? For generations, we have been shown a familiar diagram. The Sun fixed at the centre, planets circling in clean, flat rings. It is useful for teaching basic motion, but it quietly hides something essential. Space does not come with a floor beneath it or a ceiling above it. The solar system is not a flat arrangement. It is a three-dimensional region embedded in a much larger, moving environment. It is true that the planets follow paths close to a shared surface known as the ecliptic plane. You can think of it as a thin, invisible sheet slicing through space, where most planetary motion happens. But this sheet is only a small fraction of the system's full extent. Above it and below it, space continues without interruption, populated by objects, particles, and forces that rarely appear in simplified diagrams. Here is a useful comparison. Imagine looking at a city map that only shows roads but omits buildings, bridges, and underground systems. You would understand how to move from one place to another, but you would miss most of what the city actually is. The flat solar system diagram works in much the same way. Now consider a deeper layer of reality. This entire planetary plane is not even aligned with the galaxy that contains it. It is tilted by roughly 60 degrees relative to the broad disk of the Milky Way. That means the flat solar system you learned about is already angled within a far larger structure, and it does not remain still. The solar system is in motion, travelling through the galaxy at significant speed. In fact, it is drifting upward relative to the galactic plane at about 7 kilometers per second. That is not a trivial movement. It means that even as planets orbit the Sun, the entire system is simultaneously shifting through space. A small teaching insight here. When we study motion in astronomy, we often stack movements on top of each other. Earth orbits the Sun orbits the galaxy, and the galaxy itself moves through the universe. No single diagram captures all of these layers at once, so the flat image is not wrong. It is incomplete. It is the first step, not the full picture. Once we move beyond that simplification, a far more structured and dynamic environment begins to appear. And to understand that environment, we must do something very simple, yet rarely imagined. We must leave the plane entirely and look upward into the outer limits of the Sun's influence. What lies beyond the planets? Does the solar system simply end once we pass Neptune? As we move away from that familiar planetary plane, the sense of distance begins to change in a way that is difficult to grasp at first. If you were to travel straight upward from Earth, not along the usual orbital paths but perpendicular to them, your journey would still pass known landmarks. The Moon would fall behind you in a matter of hours. Mars, depending on its position, would take months. Neptune, the outermost major planet, would require close to a decade of continuous travel with current spacecraft speeds. At that point, it would be reasonable to assume you have reached the boundary of the solar system. After all, the planets define most of what we are taught. But this is where a useful correction must be made. The planets do not mark the edge. They are simply the most visible components within a much larger domain governed by the Sun's gravity. Beyond Neptune, the structure begins to thin out, but it does not end. Instead, you enter a region known as the Kuiper Belt. This is a broad, flat collection of icy bodies, remnants from the early formation of the solar system. Pluto is one of its most well-known members, but it is only one object among many thousands. A helpful way to think about the Kuiper Belt is as a distant extension of the planetary plane. It still carries the signature of that flat structure we discussed earlier, but the objects are smaller, colder, and far more widely spaced. Moving farther outward, the order begins to loosen. You encounter what astronomers call the scattered disk. Here, the orbits are no longer neatly aligned. They tilt at steeper angles, stretch into elongated paths, and reflect past gravitational interactions with the giant planets. Teaching insight. When a system becomes less orderly, it often tells us about its history. The scattered disk preserves evidence of earlier disturbances, particularly from Neptune's migration in the early solar system. And then, at distances so large that our usual comparisons begin to fail, the geometry changes entirely. Up to this point, everything has roughly followed a flattened arrangement, But beyond the scattered disk, the structure is no longer best described as a disk or a ring. Instead, it becomes something far more symmetrical. Imagine stepping far enough away that direction itself loses its usual meaning. Above and below begin to blur into a single concept: surrounding. What emerges at that scale is not a band, but a vast, spherical region enclosing the entire solar system. This transition is critical. It marks the point where the familiar, structured layout gives way to a boundary that is diffuse, extended, and largely invisible to direct observation. And it is precisely in that distant, spherical domain that the next layer of our understanding begins to take shape. As that distant, spherical region begins to take shape in our understanding, a natural question follows. How do we study something so vast that it cannot be seen directly? What we are approaching is known as the Oort cloud, a structure that defines the true outer boundary of the Sun's domain. Unlike the regions we have passed so far, this is not a belt or a disk. It is a spherical shell, extending in all directions and enclosing the entire solar system. To appreciate its scale, we need to shift our sense of distance once again. The inner edge of this cloud begins at roughly 2,000 times the distance between Earth and the Sun. Its outer limits may reach as far as 100,000 times that distance. At that point, you're nearly halfway to the nearest star. This is no longer a local neighborhood. It is a transition zone between stellar systems. Inside this immense volume, scientists estimate the presence of trillions of icy bodies. These are not large planets or even typical asteroids. Most are small, frozen remnants left over from the earlier stages of solar system formation. They have remained largely unchanged for billions of years. Here is the important complication. No telescope has ever directly observed the Oort cloud. There are no clear images, no resolved objects at that distance. So how do we know it exists? The answer comes from careful observation of long-period comets. These are objects that enter the inner solar system on extremely elongated paths, taking thousands or even millions of years to complete a single orbit. Crucially, they do not arrive from a single direction. They appear from all angles, above, below, and from every side. Teaching insight. When observations show no preferred direction, it often indicates a spherical distribution. This is a common method in astronomy, inferring structure from patterns in motion rather than direct imaging. The trajectories of these comets point back to a distant, roughly spherical source. That source aligns precisely with the predicted location of the Oort cloud. At this boundary, the Sun's gravitational influence becomes increasingly fragile. Nearby stars, passing clouds of gas, and the broader pull of the galaxy begin to compete with it. The result is a region that is not stable in the usual sense. It is constantly being disturbed, even if those disturbances are subtle and slow. And occasionally, one of those distant objects is nudged just enough to begin a long inward journey. It is from this quiet, distant boundary that some of the most dramatic visitors to the inner solar system originate. From that distant and unstable boundary, the next step in our story is not outward but inward. When an object in this remote region experiences even a slight disturbance, its balance changes. The pull from the Sun, though weak at such distances, begins to dominate its motion once again. What follows is not a sudden fall, but a slow and gradual inward journey that can take thousands of years. At first, the motion is barely noticeable. The object drifts, then accelerates, tracing a long, stretched path toward the inner solar system. Over time, this path becomes more defined, and the object transitions into what we classify as a long-period comet. These comets are fundamentally different from the regular, short-period comets that remain closer to the Sun. Their orbits are vast and highly elongated, often taking tens of thousands of years to complete a single cycle. More importantly, they do not follow the organized structure we observed earlier. They can arrive from any direction. Some descend from far above the planetary plane, others rise from below. A few even move in directions opposite to the motion of the planets. This randomness is not accidental. It is direct evidence of the spherical region from which they originate. Teaching insight. When incoming objects show no alignment with a dominant plane, It confirms that their source is not a disk, but a three-dimensional distribution. In this case, the behavior of comets becomes a map of a region we cannot see. As these objects approach the Sun, a transformation begins. The increasing heat causes their icy surfaces to sublimate, releasing gas and dust. This creates a glowing envelope known as a coma, and often a long tail that can stretch millions of miles through space. A useful comparison is to think of dry ice placed in a warm room. It does not melt into liquid first. It turns directly into gas, creating a visible cloud. Comets behave in a similar way, though on a far larger scale. Historical examples such as Hyakutake and Hale-Bopp provided clear demonstrations of this process. Their brightness and extended tails made them visible even to the naked eye, offering rare glimpses into material that has remained largely unchanged since the solar system's formation. These objects are not just visual spectacles. They are physical samples from regions we cannot directly reach, carrying chemical signatures from the earliest stages of planetary formation. And yet, an important question remains. If objects can enter our system from all directions, are all of them truly part of it? The answer begins to shift as we consider visitors that do not return at all. That question now becomes unavoidable. Are all incoming objects truly bound to the Sun, or do some simply pass through without belonging at all? The answer emerged only recently, and it required careful observation rather than assumption. In 2017, astronomers detected an object moving through the solar system with an unusual trajectory. It did not follow a closed orbit. Instead, its path was open, entering from one direction and continuing outward without turning back. This object was named Oumuamua. Its speed alone provided the first clue. It was moving too fast to be captured by the Sun's gravity. Even at great distance, where gravitational influence is weaker, bound objects must still follow curved paths. Oumuamua did not. Its motion was essentially a straight line, slightly bent by the Sun as it passed. A useful way to understand this is to imagine throwing a ball near a hill. If it is slow, it will curve around and roll back. If it is fast enough, it will pass by and continue onward. Oumuamua behaved like the second case. It was never part of the system. 2 years later, a second object confirmed this was not an isolated event. Comet Borisov entered the solar system on a similar hyperbolic path. Unlike Oumuamua, it displayed a visible coma and tail, making its nature easier to identify. But its origin was the same. It came from beyond our solar system. Teaching insight, astronomers classify such trajectories as hyperbolic, meaning the object's energy exceeds the binding energy of the Sun. This is a precise mathematical way of saying it cannot be captured. What is particularly important is the direction of entry. These interstellar objects do not align with the planetary plane. They arrive from above, below, and at every possible angle, passing through the system briefly before continuing their journey through the galaxy. This reveals a larger truth. The region surrounding the solar system is not empty or isolated. It is part of a dynamic environment where material from different star systems can move freely. You can think of it as a corridor rather than a boundary. The Sun's domain exists within a wider flow of matter, where objects occasionally cross paths without ever becoming permanent members. And yet, despite this openness, there remains a structure created by the Sun that defines a kind of protective limit. To understand that boundary, we must now shift from solid objects to something less visible, but far more influential, a continuous stream of particles flowing outward from the Sun itself. That outward flow of particles now becomes central to our understanding of how the Sun defines its presence in space. Unlike planets or comets, which are discrete objects, the Sun continuously emits a stream of charged particles in all directions. This stream, known as the solar wind, does not travel a short distance and stop. It expands outward, filling space and carrying the influence of the Sun far beyond the visible boundaries we have discussed so far. As this flow continues, it creates a vast region surrounding the solar system, a kind of extended environment shaped not by solid matter, but by moving plasma. This region is called the heliosphere. It is not perfectly spherical, but it surrounds the Sun in all directions. forming a protective envelope that extends far beyond the orbit of Pluto. To understand its scale, consider this. The heliosphere stretches to roughly 120 times the distance between Earth and the Sun in certain directions. That is far beyond the planetary region, and well into the outer domains we have already explored. Eventually, however, even this outward pressure meets resistance. Beyond a certain point, the solar wind encounters the thin gas and particles of interstellar space. At this boundary, the outward push of the Sun balances with the inward pressure of the surrounding galaxy. This creates a transition zone known as the heliopause. Teaching insight: boundaries in space are rarely sharp edges. They are regions of interaction where forces balance rather than stop. The heliopause is one such region, marking a shift in dominance rather than a hard limit. This boundary was not just theoretical, it has been crossed. In 2012 and again in 2018, the Voyager 1 and Voyager 2 spacecraft passed through this region, providing direct measurements of the transition from solar influence to interstellar space. Their data confirmed what had long been predicted. The importance of the heliosphere extends beyond structure. It plays a critical role in shielding the inner solar system. High-energy cosmic radiation, originating from distant stars and violent galactic events, is partially deflected by this moving barrier of solar particles. Without this protection, the environment near Earth would be far more hostile. Radiation levels would increase significantly, affecting atmospheres and potentially altering the conditions necessary for life. So while earlier we considered objects moving through space, here we see something different, a continuous interaction between the Sun and its surroundings. And beyond this protective boundary, the environment changes once again. The solar system is no longer defined by its own processes alone, but by the properties of the region it is moving through. To understand that larger context, we must now examine the immediate galactic environment that surrounds this entire structure. Beyond that protective boundary, the environment does not become empty. Instead, it changes character. The region immediately outside the heliosphere is known as the local interstellar cloud. It is a thin mixture of gas and dust, far less dense than anything we experience on Earth, yet significant on astronomical scales. The solar system is currently moving through this cloud, carrying the entire heliosphere along with it. To understand its nature, it helps to adjust expectations about density. Even in this cloud, particles are extremely sparse. In a volume the size of a room, you might find only a few atoms. Yet over vast distances, this sparse material becomes a meaningful environment that can influence large-scale structures. This local cloud is not isolated. It exists within a larger region called the local bubble. This bubble is thought to have formed from multiple supernova explosions that occurred millions of years ago. Those events cleared out much of the surrounding material, leaving behind a cavity filled with hot, low-density gas. Teaching insight: in astronomy, absence is often the result of past activity. A region that appears empty can be the aftermath of extremely energetic events. As the Sun travels through this environment, the properties of the surrounding medium begin to matter. The density and pressure of the interstellar gas can affect the size and shape of the heliosphere. In denser regions, the external pressure increases, compressing the heliosphere inward. In less dense regions, it can expand outward. This is not just a theoretical idea. There is evidence suggesting that in the distant past, the solar system may have passed through regions of higher density. Such encounters could have reduced the heliosphere's size, allowing more cosmic radiation to penetrate toward the inner planets. A useful comparison is a ship moving through water. In calm conditions, the boundary around it remains stable. In rough or dense conditions, that boundary shifts and compresses. The heliosphere behaves in a similar way as it moves through different interstellar environments. What is important here is that the solar system is not isolated. It is embedded within a changing galactic context, where external conditions can influence internal stability over long timescales. And all of this activity, clouds, motion, and interaction, takes place within an even larger structure that defines the broader stage on which our system exists. To fully understand that structure, we now need to step back once again and examine the galaxy that contains all of it. That larger structure now comes into view as we step back even further, beyond local clouds and protective boundaries, into the full scale of the galaxy itself. The Milky Way is not a random collection of stars. It is an organized system, shaped like a vast disk stretching roughly 100,000 light-years across. Most of its stars, gas and dust, are concentrated within this flattened plane, forming the familiar spiral structure observed in distant galaxies. However, this disk is only part of the picture. Above and below it lies a much more diffuse region known as the galactic halo. Unlike the dense plane of the disk, the halo contains far fewer stars, but those it does contain are among the oldest in the galaxy. Many are grouped into spherical clusters known as globular clusters, which orbit far above and below the central plane. In addition to these visible components, the halo is also believed to contain a large amount of dark matter. This unseen mass does not emit light, but its gravitational influence is essential for holding the galaxy together. Without it, the outer regions of the Milky Way would not remain stable. Teaching insight. In large systems, what we cannot see often dominates what we can. Dark matter is a prime example, shaping the motion of stars without being directly observable. Our solar system is not located at the center of this galaxy. It resides slightly above the galactic plane, orbiting the center along with billions of other stars. But this motion is not limited to a simple circular path. Over long periods, the solar system also moves up and down relative to the plane in a slow vertical oscillation. This vertical motion occurs over tens of millions of years. As the solar system passes through different regions above and below the galactic disk, the gravitational environment changes subtly. Some scientists suggest that these oscillations may influence the rate at which distant objects are disturbed, potentially affecting the number of comets entering the inner solar system. A useful comparison is to imagine a buoy moving up and down on the surface of water, while also drifting horizontally. The motion is layered, with each component adding to the overall path. The solar system behaves in a similar way within the galaxy. What emerges from this perspective is a system that is not fixed, but constantly moving within a larger structured environment. The Milky Way itself is dynamic, evolving over time as stars form, interact, and sometimes explode. And yet, even this immense galaxy is not isolated. To complete our understanding, we must extend our view once more, beyond the Milky Way, into the interactions between galaxies themselves. That broader stage now brings us to a final, unavoidable realization. Even galaxies do not exist in isolation. The Milky Way is part of a larger collection known as the Local Group, a small cluster of galaxies bound together by gravity. Among them, one stands out both in size and in consequence. The Andromeda Galaxy, comparable in scale to our own, is not stationary. It is moving toward the Milky Way at a speed of roughly 250,000 miles per hour. At first, this motion may seem abstract. The distances involved are so vast that no immediate change is visible. But, in astronomy, time operates on a different scale. What appears static within a human lifetime can represent an ongoing process when viewed over billions of years. Based on current measurements, these two galaxies are on a collision course. In approximately 4 to 5 billion years, they will begin to merge, gradually combining into a single, larger galaxy. Teaching insight. In galactic interactions, the term collision can be misleading. Unlike solid objects, galaxies are mostly empty space. The distance between stars is so large that direct star-to-star collisions are extremely unlikely. Instead, the interaction is governed by gravity acting on entire systems. As the galaxies approach, their shapes will distort. Long streams of stars and gas will be pulled outward, forming extended tidal structures. Over time, their original spiral forms will be disrupted, eventually settling into a new configuration. The most significant changes will occur in the gas clouds within each galaxy. When these clouds interact, they can compress, triggering intense bursts of star formation. Entire new generations of stars will emerge as a direct result of this process. A useful comparison is the merging of two weather systems. The individual air currents do not collide as solid objects, but their interaction produces large-scale changes, including storms and shifts in structure. Galaxies behave in a similar way, though on a far greater scale. From the perspective of any future observer within the solar system, the night sky would undergo a profound transformation. The familiar patterns of stars would gradually shift, and the Andromeda galaxy would grow larger and more detailed over millions of years. What is essential to understand is that this is not a hypothetical scenario. It is a predictable outcome based on observed motion and well-established gravitational principles. And even this event, immense as it is, does not represent the larger structure in which our galaxy participates. To complete our journey, we must now step beyond individual galaxies and examine the vast patterns that organize the universe itself. That larger pattern now forces us to take one final step outward, beyond galaxies themselves, into the structure of the universe at its widest scale. When we observe the distribution of galaxies across vast distances, an important pattern emerges. They are not scattered randomly. Instead, they form extended structures, long filaments and broad sheets, connected across millions of light years. Between these structures lie enormous regions with very few galaxies at all. These are known as cosmic voids. To understand this arrangement, it helps to imagine a three-dimensional web. The galaxies trace the threads, gathering along dense intersections, while the empty spaces form the gaps between them. This is often referred to as the cosmic web, a structure shaped by gravity over billions of years. Our own galaxy appears to lie near the edge of one of these voids. This position is not unique, but it is significant. It means that on the largest scales, the Milky Way is part of a boundary region between denser clusters and more empty space. Teaching insight. In large-scale systems, emptiness is not simply the absence of matter. It plays an active role in shaping motion. In this case, matter is pulled toward dense regions, while the relative lack of mass in voids allows them to expand, effectively pushing galaxies away. This creates a continuous large-scale movement. Galaxies drift along the filaments, drawn toward clusters, while voids grow over time. The result is a dynamic structure that evolves slowly but consistently across the age of the universe. A useful comparison is the distribution of bubbles in a rising foam. The material collects along the boundaries between bubbles, while the interiors remain mostly empty. Over time, the structure shifts, but the overall pattern remains. What becomes clear at this scale is that most of the universe is not filled with stars, planets, or even gas. It is dominated by vast regions of near emptiness. Yet this emptiness is not without consequence. It defines the paths along which galaxies move and the locations where structures form. If we now reflect on everything we have traced, from the planetary plane to distant comets, from the Sun's protective boundary to the motion of galaxies, we see a consistent theme. Every layer exists within a larger framework, and each framework is shaped as much by what is absent as by what is present. Above and below, in every direction we have explored, there is no final edge. There are only transitions, from one structure to another, from one scale to the next. And beyond even this cosmic web, the universe continues, extending past the limits of what we can currently observe, leaving open questions that remain for future discovery.